Last time we talked about the simplex method, right? To solve linear programming. Okay. Well, we have done with the two-phase algorithm also, right? Okay. We start from the most simplest one. It's a simplex method. And then we learned that for simplex method, of course, you need a problem in a specific form, right? For example, all the of course, for objective function, it can be maximized or minimized because it's really easy to convert back and forth, right? Between maximum and minimum. But for the constraint, we need a constraint in a canonical form, right? Where the right-hand side, the constant at the right-hand side must be positive, okay? Non-negative, sorry, not strictly positive, non-negative. It can be zero, it's of course. And for here, the relationship here must be canonical form. It's a lesser or equal, okay? Lesser than or equal. Must be in strict, very strict form for the simplex method. And if not, we need two-phase algorithm, right? And for two-phase algorithm, of course, you can handle the problem where no, this one is the simplest method. It's for example, this one, where we have equality constraint, right? In case we have equality constraint, it's very simple. You just add extra variable, auxiliary variables, right? And for greater than or equal, this one, right? This one is lesser than or equal. However, at the left-hand side, the constant at the right-hand side is negative. So you multiply this inequality with negative, right? -1. And of course, you obtain -2, right? -2x1 minus x2 plus 2x3, right? And the relationship here must be greater than or equal, right? And on the right-hand side, it is 4, okay? Then you need extra variables, and you have to subtract it by slack variable, right? Okay. Then you solve the two-phase algorithm by at the phase 1, our task is to remove all the E variables, extra variables, auxiliary variable, okay, from basic variable. And we have to guarantee that W must be 0, right? W is the sum of all E variables, okay? Okay. I hope that you can still remember that, okay? So, of course, last time I showed you several example, but must be, well, we went very fast maybe because I have done that before. So now it's your turn. I have several example, and then you can solve it by yourself. Okay, starting from this one first. We have maximize 6x plus 7y, okay? And we have following constraint. 7x plus 6y lesser than or equal 42. 5x plus 9y lesser than or equal 45. X subtract by y, okay? X minus y lesser than or equal 4, okay? And luckily, all X and Y are non-negative, okay? So you see that this problem can be solved by simplex method, okay? Just phase two, okay? You don't need two-phase algorithm, right? Because all constraints are in canonical form, right? And the right-hand side is, they are all positive, right? Okay, lesser than positive. Okay, all you have to do is, first, we add slack variable, right? Add S1 here, okay? And then this relationship becomes equal, okay? We add S2 here, okay? Select variable number 2, and it becomes equal, okay? Here also plus S3 and then equal 4, okay? Good. Then solve it. Why are you waiting? Yeah, just open Excel and then solve it. Yes. Pardon? Which page in the slide? In the slide I gave you before, right? No. I just add extra page. Okay. So, well, you see, this is my Excel. And I suppose that you can do it by yourself, okay? The next problem, you will do it by yourself, okay? You have to do it by yourself. So, you see, we have X, Y, right? S1, S2, S3, okay? And 7, 6 is their coefficient, okay? From the first inequality constraint, okay? And we add S1, okay? So it should be 1 here, right? And on the right-hand side, it's 42, okay? Good. And the second constraint, the coefficients are 5, 9, right? And because we add S2 to this inequality, of course, no S1, then it should be 0. And 1 here because we add S2, okay? And for S3, it's 0, right? And right hand side is 45, okay? Okay, so for the third one, the third equality constraint, the coefficients are 1 and -1, right? Okay, and we add S3 here, so it should be 1 here, okay? And the right hand side is 4, okay? And for the objective function, the minimization form of it, the coefficients are -6, -7, right? Okay, and it is 0, okay? So, which is the pivot row? Oh no, column, not row, pivot column. The pivot column, we consider the most negative coefficient of the objective function, right? Which is the coefficient of y, this one, right? Which is -7, okay? So in the next round, we add y to our set of basic variables, okay? And because the number of all basic variable must be 3, okay? And at the now we have S1, S2, S3 as our basic variable. If we want to add y as our new basic variables, we have to remove one basic variable, right? The original basic variable. And the one we're going to remove, we consider b over a, right? The ratio, the fraction of b and a, okay? This column, b, it's 42 divided by 6. And this one, it's 45 divided by 9, right? Okay. But actually, this one we can skip because this is already negative. Okay. We consider only positive one. Okay. So which one is the variable we're going to remove from basic variable? S2, right? Because this is the smallest, okay, positive one. Okay. So in the next round, we're going to add y as basic variable, and we remove S2 from our basic variable, okay? In the next round, our basic variable becomes S1, y, and S3, okay? Okay, so this is the pivot element. So we need row operation, yes. We divided all this row by 9. Okay, then we obtain 1 here. Okay, what else do we need? We need to, well, the metric where this element must be 0. This 1, right? 0, 0. Okay, so we start from this. Divided this row by 9. Okay, divided by 9. Okay, you obtain this table. Okay, this table. You see? Okay, this table. And then how to make this element 0? How to make it 0? How to do it? From this row, you subtract it by 6 multiplied by this row. You multiply 6 to this row and subtract the first row. Okay? Okay? So you see, here, we multiply this row B8 by 6, right? And then we subtract it. We subtract the row number 7, okay? Okay, good. So you will get 0 here. Okay? Repeat the same algorithm, okay? For each element here. And then the second row, just copy, okay? Because we have 1 here already, so just copy. And for this row, okay, you start from this row and you subtract it by, you multiply -1 to this row and subtract it to subtract with this row, okay? Then you obtain 0 here, okay? For the last one, this one, we need 0 here also. You multiply -7 to this row and you subtract all this row. Okay? Do it, repeat it. Yeah. Try to do it by yourself and you will understand. Okay? You will understand the algorithm. And then you will get this row, no, this table. Okay? Once you obtain this table, it's not finished yet, right? Because we still have negative coefficient. Then what are we going to do? This is pivot column, right? And then we consider B over A, okay? The ratio of B over A, okay? And then we see that this is the pivot element because this is the smallest positive ratio of B and A, okay? So this column is X, right? So we're going to introduce X as our new basic variable, and we going to remove S1 from our basic variable. So for the next round, we have X, Y, and S3 as our basic variables, okay? Okay, then you repeat it the same from this table because this is pivot row. So we make this element to be 1 and the rest becomes 0, okay? Divided by this value for the whole row, okay? You will get 1 here, okay? And then how to make this element 0? You multiply the first row, this row, by 0.555556, okay? And then you subtract it. You will get 0, okay? Again, how to make this row, no, this element to be 0? You multiply 1.555556 to this row and you subtract this row, okay? You multiply this row with this value, minus 2.111, okay? And subtract this row, you obtain 0, yeah? Okay? Do it yourself. Finally, you get this one, this table, okay? And this table, you see that we cannot further decrease the objective function because we don't have negative coefficient anymore, right? So that means this is the optimum point, okay? So here our basic variable is X, Y, and S3, okay? X is this value, Y is this value, S3 is this value. What about S1 and S2? S1 is 0, S2 is 0 also, okay? That means the first inequality and the second inequalities are active, right? Okay. Active means, well, it's not lesser than or equal anymore. They both becomes equality constraint at that point. Okay. Okay. Do it by yourself. Well, you have 10 minutes to do it. Huh? Pardon? The last one, which one? This one? Right side, this? My left, yeah. Up. This. This is right, not left. Yeah, you said left. Yeah, this is right. On the right side. Yes. What will be the order for writing this? Like first we have to write yeah, you can write this value. This one it's this value, right? Because this is x, y. S1, S2, it's the S1 is 0, S2 is 0. Yeah, you don't have to write it, but I just tell you where we are now. Okay. You see that at the first place also at initial, I write 0, 0, 42, 45, 4. That means we are at the x is 0, y is 0, right? S1 is 40, 42, S2 is 45, and then S3 is 4. Okay. Okay, do it by yourself. Okay, I show you that screen first and then you capture it. Okay, then take, yeah, take photo. Oh, this is quite simple example, okay? The purpose is to improve your understanding of the algorithm. So, of course, if you have any, well, any things that you don't understand or anything confusing, yeah, just just ask, okay? Why you use the same one computer only? Okay, all right, all right, all right. But actually, even iPad, you can use Excel in your iPad to solve this. Any questions? Okay, so okay, look at, yeah. What I'm doing is normally when you did once you determine the pivot element, the pivot element is here, right? Okay, I just copy everything first, copy everything. Okay, but because this row is our pivot row, right? So it must be, okay, divided by C3, right? And this one must be constant, okay? Even you copy it, it must be constant, not change, right? Okay, so we obtain this, right? And then in order to make this element to be 0, we subtract this one by this one time with, right? You get it? Subtract 6 by this one time with this one, okay? And then you copy, okay? The next row, because this is our pivot row, we don't do anything, okay? And the next one, we must, this element must be 0, right? So we start from this one, subtract by this element. No, not that is that row, this row, time with this element. Okay, good. So we copy it. The next one, this one, subtract by this one, time with this one, but this must be constant. Okay. Okay. Then we obtain, right, our table in the second iteration. Of course, if you don't like Excel, you can use Python. I give the Python file already in my course view. This one is our pivot column, right? Because the coefficient is negative. Okay. All you have to do is calculate the B over A, right? Ratio of B and A. How to do it? Just B, right? B here, B and A. Yes, B and A. Okay. And then this is the smallest positive. Yes, this is the pivot element. Okay. The next table, you just copy it first and then divide it by this element for the whole row divided by this element. Okay. So you get 1 at this position. Okay. You can do it by yourself, right? Okay, good. Yes. Which one? To make it 0. Where is it? Here, right? Okay. Yeah. Yes.
I can't hear your voice well.
You can hear me now?
Yes, Ajay.
I'm sorry. I speak to microphone, but I turn microphone off. Yeah, I just noticed that. Sorry. Okay, so that is the reason why we need zero coefficient here. Okay, if it's not zero, we have problem because we have two variables. So we don't know the value of S1 from this one. If we force this coefficient, the 6 to be 0, then we know this column, the value at this of this column is S1. Okay. So that's the reason why when we identify, we determine the pivot element, then only the pivot element, the coefficient is 1, and the rest in that column, the coefficient must be 0. No, different. The objective function. Yeah. Yes, the power. Yes. No, you cannot do it in timetable, just on that column. Yes. And you see that, for example, the first one, the first one that you mark, highlight, green, is no. The upper table, yeah. You see, our basic variable is S1, right? And you see that only his element is 1. The rest is 0. S2 is our basic variable. Only is 1. S2 is 1. The rest is 0. S3 again, 1. The rest is 0. Every time you change, yes, yes. Once you change the basic variable, you have to go out and add that column. Only your basic variable. Yes, right. Okay. And I will show you the solution. Okay. This is the solution. Okay. We have coefficient of minus 13, right? 19, sorry. Minus 19. Here is a pivot column. And this is our pivot element. Okay. Luckily, this is 1. So you don't have to divide by anything. But you have to, well, do the sum operation in order to make this coefficient to be 0, 0. And this must be 0 also. Okay. Then, yeah. This is the second term. Okay. 0, 0, 1, 0. Okay. Then the coefficient is negative here. Okay. So this is our pivot column. And we consider this element is our pivot element. And we divide this row by 13 in order to make it 1. Okay. And then we obtain this, right? You multiply by this row by 14 and you subtract it with the second row, okay, to obtain 0. Okay, again, this column, this row, you multiply by -1 and subtract with this row in order to obtain this row. Okay. In this one also, you multiply this row by -26 and subtract. Yes, every yeah column. Once you subtract it, you got 0. When I say multiply the row, you see, actually each row is one equation. You cannot multiply by only one place, one element. If you multiply any row by any number, of course, you have to multiply all, right? Because it's equation. Okay. Also, when you subtract the row by row, of course, it's simply, you cannot subtract by only single element. You have to subtract by the whole row, okay? In order to preserve the equality, okay? Okay, then you obtain this finally. And this is the result. Our coefficient is positive, then we stopped. And this element is the optimum value of our objective function, okay? Okay, we move to the next one, the next example. This one. For this one, maximize x plus 2y, right? The first equality constraint. No, inequality constraint. X minus y is greater than or equal minus 8. This one, it's actually you multiply by -1, then this greater than or equal becomes lesser than or equal, and this is positive. Everything is okay. But the second inequality is greater or equal is 0. Okay, you can handle, you can change it to lesser than or equal 0. It's okay because 0 is 0. And the next one, x plus y is greater than or equal 8. This one you cannot multiply by negative anymore because the right hand side is positive already. Okay, so this one emphasize that it translates that you need two-phase algorithm, right? You need two-phase algorithm. Why? Because this is greater or equal and positive. Right hand side. And the fourth one, of course, at the right hand side, we have positive value. All right. But this is a greater or equal. That means, wow, you need special treatment. You need two-phase algorithm. And The next one. It says lesser than or equal 86. Okay, no need. Two-phase algorithm. But of course, it's render that the whole problem need two-phase algorithm for sure. Okay. For the first one, you need S1, right? You need slack variable. You have to add slack variable. The second one, if you treat it this way, greater than or equal, you need extra variable, and you have to subtract it by slack variable also. Okay. And the third one, you need extra variable, and you have to subtract it by slack variable. Okay. What about the fourth one? Again, the same. You need extra variables and subtract by slack variable. This one you have to introduce slack variable, and the last one you have to introduce one slack variable. Okay. Okay. So solution for that one. Yeah. And you see that we, of course, from the first inequality constraint, the first constraint, we need select variable, right? S1. And for the second one, we add E1 and subtract by S2. Okay, we add E1 here, 1, and subtract by S2. Okay. And the next one, we add E2 and subtract by S3. Okay. Keep going on this. Okay. And we have to consider objective function and W. Okay. But for phase one, we consider W first. Our aim for the phase one is to remove the extra variable from basic variable. Okay. Our basic variable must not contain E variable, extra variables. Okay. So we look at this most negative coefficient first and find the pivot element. This is pivot element. Okay. We use the same trick. Divide this row by 6. Okay. And change this coefficient. Other coefficient in the same column must be 0. Okay. This must be 0, 0, 0. And this must be 1, right? 0, 0, 0, 0. Okay. Then we obtain this. Okay. You see that we in the first iteration, we introduce Y to basic variable and we remove, I don't know, what is it? E3, right? E3. Mm-hmm. And the next one is, of course, this is the negative. We introduce X to basic variable and we're going to remove E1, okay? Do the same thing here. Okay, you see, at this route, our basic variable contains S1, X, E2, Y, S5, S6, okay? Not finished yet because these coefficients, we still have negative coefficient. We choose this column because this is more negative, and this is our pivot row. We going to introduce, this is X, Y, S1, S2, right? S2. And we remove E2, okay? We obtain this, okay? We remove E2. We introduce S2. And from here, you see that W, this table, indicate W is 0. Oh, okay. W is 0. And we don't have negative coefficient. Also, our basic variable, the set of our basic variable does not contain E variables. Okay, that means, well, we can enter to phase 2. Okay, we remove this row. We remove all the column for E1, E2, E3. Okay, so the table reduced to this table where we remove all W coefficient, and also we remove all E variables. Okay. Now we consider the objective function. We can further decrease. We can further reduce the objective function because we have negative coefficient. Okay. This is the most negative. So this is our pivot column. And this is our pivot element. Okay. We introduce X, Y, S1, S2, S3. Yeah, we introduce S3 and we remove S6 from basic variable. Okay. Then the next round we have basic variable of S1, X, S2, Y, S5, and S3. Okay. We still have negative coefficient here. So we remove this. Now we introduce G. What is G? G is S4. We introduce S4 as our basic variables, and we remove S5. Okay. So the next round, we have this table. Our basic variables contains S1, X, S2, Y, S4, and S3. We still have negative element here. Okay. We introduce S5. No, S6. Okay. And we remove this S1. Okay. You do the same. Follow the same idea. Then you obtain this table. Okay. And this table is finished because you don't have negative coefficient anymore. Okay, you stop. And this is our objective function, the value of our objective function, the optimum value. Okay, where X is this value and Y is this value. Okay. S1 and S5 are active. Okay. Okay. So try to do it by yourself. Yes. Which step? The first step. Then we write objective function. W. Yeah, the W. How to write W? Yeah. Okay. Yeah, this is how we write W. No, oh, sorry. because W is summation of all E variables. We have E1, E2, E3, right? E4, do we have E4 in that example? No, we have E1, E2, E3, right? Only 3 variables. Yes. So E1 plus E2 plus E3 is minus W must be 0, right? And then from the constraint that contains E1, E2, E3, you subtract, you substitute for E1, E2, E3 back. Okay? Hmm? The second one, 5x minus y plus E1 minus S2. S2, right? Should be S2. S1 used in the first 0. Okay? What else do we have? We have x plus y plus E2 plus E2 minus S3. Okay? Equal 8. Right? The next one is minus x plus 6y plus E3 minus S4 equal 12. Okay, good. Okay, the rest, we don't have E1, E2, E3. We have E1 plus E2 plus E3 minus W comes 0. Then you sum all of this, okay? What do we have? Huh? You sum all of this 5x, right? Because it's cancelled out. It's cancelled out. So 5x plus 6y plus E1 plus E2 plus E3 minus S2 minus S3. So equal 12, right? You sum all of this, okay? And so E1 plus E2 plus E3 equal minus 5x minus 6y plus S2 plus S3, right? What else? Plus, one moment, plus 12, 20, okay? Okay? Right. So substitute back here. We have 5 minus 5x. Okay. Right? So what do we have? Minus 5x minus 6y plus S1 plus, no. Yeah. Yes, 2, 3, 4. Minus W equal minus 20. And look at the Excel. You see, minus 5, minus 6. What about S1? S1 is 0, right? S2 is 1, 1, 1. 0, and then 0, 0. And then minus 20. Okay. Maybe they down. Okay. That Excel, I will upload that Excel later. Okay, now we move to the last topic in the linear programming. It is duality. We call it duality. Let's say we have problem, original problem, we call primum problem. We can convert it to duality of that problem, okay? And duality is, it's a, what is it, one-to-one conversion. Once you convert original problem to the duality, and you convert again, you will obtain the original problem. Okay. For example, we have this linear programming. A11x1 plus A12x2 plus blah, blah, blah. Greater or equal B1. Okay. And you have objective function in a minimization form of C1x1 plus C2x2 plus this. Yes. And all x decision variables is non-negative. Okay. You can convert it to this problem. Okay. This is duality of that problem. The constraint contains A11Y1, A21Y2. Yes. Lesser or equal C1. Yeah, C2, C3 to Cn. Okay. And the objective function is in maximized form of B1Y1 plus B2Y2 plus and so on, BMYM. Okay. And all Y variables are restricted. Okay. Non-negative. And you see the constant at the right hand side, C1, C2, Cn in this problem are coefficient of the objective function in the original problem. Okay. And you see the right hand side constant in this original problem are the coefficient of the objective function of the duality. Okay. And also the coefficient, the A matrix. Okay. A11, A21 here. So appear here. Okay. But problems, the primal and duality. Okay. So let us compare primal and duality. We have primal problem in this form, minimize of something. Yes, when we have set of constraint, okay, where Aij xj equal Bi and Aij xj greater or equal Bi. Okay. Once we convert it to duality, from minimize, we obtain maximize. Maximize of Yibi. Okay. Where is B? B is from here, the right hand side of the constraint. Okay. And see here, the right hand side in the duality is exactly the coefficient of the objective function. Okay. But here we have greater or equal, right? The duality of it must be lesser or equal. Okay. And the objective function in primal, it's a minimization, but duality must be maximization. Okay. Why do we have to learn this thing? Okay. But before we going to learn about property of the duality, let me show you example. Okay. For example, we have primal problem here. Maximize 50x1 plus 100x2. And we have this constraint. 2x1 plus x2 lesser or equal 1,000 and 250. Okay. 2x1 plus 5x2 lesser than or equal 1,000. 2x1 plus 3x2 lesser than or equal 900. x2 lesser than or equal 150. And all of these variables must be non-negative. Okay. We can convert it to duality where the objective function is minimize 1,250 y1, okay? 1,000 y2 plus 900 y3 plus 150 y4, okay? And the constraints, well, from 2 to 2, we have 2y1, 2y2, 2y3, greater or equal 50. Why we have 50 here? 50 here, it's a coefficient here. Okay, and the second constraint also from 1,531, right? 1,531, okay? And this is greater or equal 100 here because we have 100 here, okay? Most problems are primal and duality, okay? If on the right-hand side is your primal, of course, your duality is on your left-hand side, okay? If your left-hand side is primal, of course, this is the right-hand side is duality, okay? So, as I mentioned to you, that duality is one-to-one conversion. So the dual of the dual is the primal, okay? You got it? Dual of dual is primal, okay? You find a dual 2 times, you obtain the original one. If both primal and dual problems have feasible solution, both problems have optimum solution and minimum F equal maximum V, okay? And if either the primal or dual problem have an unbounded solution, the other problem is infeasible, okay? If you find your primal problem is infeasible, of course, you find the duality of it. The dual one, it's unbounded optimal solution. If the primal is unbounded optimal solution, the dual of it becomes infeasible. Okay? We have more example. Okay, this is dual of primal and dual. Okay. This is also, you see, 1, 1, right? We have 1, 1 here, 1, 1 here, 1, 1 here, and minus 1, 1, so minus 1, 1. Okay. This is also, yeah, primal and dual. Okay. And why we need to learn of this duality? Remember that for simplex method, we need consider the phase 2 first. For phase 2, we need a feasible solution, okay? Basic feasible solution at the beginning. If you don't have basic feasible solution at the beginning, of course, you cannot follow the algorithm. You need two-phase algorithm, right? However, we know that if the problem is infeasible in primal, the dual of it must be unbounded. And for unbounded solution, optimal solution, you can follow the simplex method, right? So people developed the dual simplex method. For dual simplex method, of course, if your Primum problem has a feasible, starting point, you don't need dual simplex method. You don't need two-phase method, right? Okay. But if not, you need two-phase algorithm, or you can use dual simplex method. Okay. Consider this problem. Okay. Minimize of 20x1 plus 16x2. Okay. For this one, of course, you see it's infeasible for the simplex method, the phase 2, because you have 2 pi phi, which is positive at the right hand side, but you have greater or equal. Okay. In order to solve this problem, of course, you need two-phase algorithm. You have to add E variable, right? E1 and subtract by S1, right? But we are not going to do that. We're going to use dual simplex method instead. Okay. So for dual simplex method, you don't care about the left-hand side. Okay? You just rearrange your inequality to this form, lesser or equal. Okay? And the right-hand side must be negative. Negative, it's all right. We will deal with it. Okay? So we follow the same idea. This is lesser or equal. So we add select variable. And this lesser or equal becomes equal. Okay? This one, right? We add S1. So from lesser or equal, it becomes equal. And the second line also, we add S2. Then this become equal, equality. Okay? And this line, we add S3. And it becomes equality, equality. Okay? And we write all those in this table. It looks similar to what we did before, right? Using simplex method. But what the difference is, previously, we never have negative value here. Okay? Okay. Now, the algorithm, instead of look at the coefficient of the objective function, we look at right-hand side of the constraint first. The simplex method, remember, you look at the coefficient, right? You find the most negative coefficient of the objective function. But remember that once you translate, you convert the primum to dual, the right-hand, the coefficient of the objective function becomes the right-hand side of the constraint, right? I can show you. Here, 50, 100 becomes, right? Also, you can consider this coefficient becomes this right-hand side, right? So once we look at this table, instead of consider this coefficient, we consider this constant instead. Find the minimum. Which one is the minimum? We call it pivot row. This is the minimum, right? Yes. Minus 17 is the minimum. This is the pivot row. Okay. Now, which column? We find minimum of C over minus A. And A must be negative, okay? Instead of B over A, we find C over A instead. Why is C over A? C, this is C, coefficient of objective function, right? We divide C by minus A. This row, C over A is 20 over 2, right? It becomes 10. C over A is 10. What about this? It's 16, right? Okay, you find the minimum one. This is the minimum one, right? So this is the pivot element. So we transform this table to this table. We follow the same idea. This element must be 1. How to make it 1? You divide this row by minus 2. Okay? And you use pivot the row operation in order to make 0 here. This 1 0 0 0. Okay? And then you obtain this table. Okay? Is it done? No, not yet. We still have negative on the right hand side. We find the most negative, the minimum one. This is minus 6. This is minimum 1. Okay? This row is pivot row. Okay? And you find this row, C over A. Okay? And A must be, no, C over minus A. Yes. And A must be negative. Okay? This is the pivot row. And this is pivot element. Okay? Then we make this element to be 1. Okay? This must be 0, 0, 0, 0. Okay? Okay? Is it done? No, not yet. We still have negative here. Is negative? Determine the pivot row. This is pivot row. We find C over minus A. And this is our pivot element. We make this element 1. And the rest must be 0, 0, 0. Okay? Okay. We obtain this. Okay? We obtain this. Then, yeah, we finish. It is done. Yes? Minus what? This one? No, no. This is the objective function value. This is the objective function value. Objective function value can be anything, right? It's not the right-hand side of the coefficient, the constraint. Okay, so you see, if, of course, the problem is in canonical form, and the right-hand side is positive, they are positive, right? Lesser than or equal and positive. You can use simplex method, very simple, right? But if it's not, if it contains equality, of course, you need two-phase algorithm. Okay. However, if it can be solved by using dual simplex method, you can do dual simplex method. Okay. But dual simplex method cannot handle equality constraint. Okay, for equality constraint, of course, you have to consider using the two-phase algorithm anyway. Okay. Okay. So it is done because linear programming using Excel. I believe that everyone can do it now, right? Because previously I show you in some example using Excel to solve it. You just define the objective function, right? Which is a function of decision variable, and you define the constraint, right? And then from solver parameters, you define the objective, minimize or maximize. But this one, I recommend you to use OpenSolver, right? Okay. And also, later you can have a look at the slide, because I explained the meaning of binding, not binding, and also the sensitivity analysis. I remember that in the class, I explained that already about allowable increase, allowable decrease, right? And also shadow price. Okay. So take your time to read it and try to understand on this. Yeah, I explained already about the meaning of shadow price and also the changing of gradient and what happened. Okay, and the rest of the slide involve the YAO-MIP. Okay, but in this class, I think we can skip YAO-MIP because I believe that you can use Python instead. Okay, for YAO-MIP, of course, if you're interested in later, you can ask me. For YAO-MIP, you need MATLAB, and of course, you have to install solver. And I recommend using Gurobi. But you can use Gurobi anyway in Python, right? So you can skip MATLAB. But if you have strong interest on MATLAB, of course, we can do YAO-MIP later. Okay. In terms of programming, this one is much easier than in Python. But if you're familiar with Python, of course, you can use Python. Okay. So any more questions for today? So the midterm, well, the content of the midterm, you finish here, linear programming. Okay. ยกคลาสคืออะไร14 oh 14วันหยุดนะ okay. Yeah, I will try to cover it with video. Yes. 20, right. 20, right. Okay. So for midterm, I think you can check in my course view. Okay, I already explained which part we will deal in the midterm exam, and what is the fraction of the mark. Okay, any questions from Zoom? No? If not, we finish today, okay? Yes? Simplex method, right? On the right-hand side, you will never get negative value. If you get negative value, then something wrong, okay? Okay, so today it's done, okay? Let us call a day.